So our first example here is the integral of the quantity x squared plus 1 all cubed 2x dx. And so you'll see here that since the innermost part of this function, or the part that's being raised to an exponent, is this x squared plus 1, I'm going to use that as my u. And then to get this du, the easiest way to think about this is if I take the derivative of both sides. So I take du dx equals, now I take the derivative of this and I get 2x, and then I can multiply the dx over here. Alright, so I get the differential of u equals 2x dx. And you can see that now I can write my integral as this part in here is u, so it's u cubed, and then everything that's left over is this 2x dx, so I can replace that with du. Alright, so I write my integral that way, and now as you can see it's a much simpler integral. Right? We don't have this product of things, we don't have this sort of the end result from the chain rule. It's all caught up, it's all taken care of just by using this simple u substitution, and now it's a very easy integral. Right? I find the antiderivative by adding 1 to the exponent and divided by the new exponent. Whenever I do an indefinite integral, of course, I have my plus c. So here's the antiderivative of my u cubed, and then the final step is going to be I'm going to replace that u with the original x squared plus 1. And there's my final answer. Right? So taking a look at the next example here, we have the integral of x squared times the square root of x cubed plus 4. So I'm going to let u equal x cubed plus 4. That's the innermost part of this function. And of course, if I take the derivative of both sides, du dx equals 3x squared, and then I multiply the dx over, so my du is 3x squared dx. Alright, so what we want to do now is this example is a little bit more complicated than the first one. So you can see here, as I try to write my integral in terms of u, I have the u here, so I could write this as the square root of u. But then what I have to replace, the leftover part that I still haven't accounted for, is this x squared dx. Right? And here I have a 3x squared dx. So what I'm going to do here is I'm going to solve this for just the part that I want to replace. In other words, the terms in this integral that I want to replace are still x squared and dx. So I'm going to solve this for x squared dx, meaning I'm going to divide by that 3. So I'm going to get du over 3, or 1/3 du, equals x squared dx. Right? So I'm going to replace this x squared dx with du over 3. Right? Now this is just a 1/3, and I can bring that out in front. So the 1/3 du, I can bring the 1/3 out of the integral. My u to the 1/2 du is still there as part of the integral. And now I can do my integration. So I add 1 to the exponent of u, divide by the new exponent. I have my plus c, and then this part I'm just going to simplify. If I divide by 3 over 2, it's like multiplying by 2/3. And I substitute my x cubed plus 4 back in there for the u. So I have, instead of u to the 3/2, I have x cubed plus 4 to the 3/2 plus c. So this is a good introduction to, you know, one of the key things that we use in u substitution, and that is trying to rewrite the integral that used to be in terms of x and rewrite it without changing its value, but rewrite it all in terms of u. And this is one way we can do that, thinking about part of the integrand we replaced with u itself, and then part of it we're going to replace with the du, but it's not exactly what we got for the du. So we have to think about what part we're actually replacing, and then replace the x squared dx with our du over 3. And that ends up giving us a 1/3 there. So we'll try that again with this example. This time we have a trig function. We're going to integrate cosine of 4x dx. So we're going to use the argument of the trig function, meaning that 4x. So we're going to use that for our u value. And then if I did the derivative of the left side is du dx, and that would equal 4. And then multiply the dx over, so the differential of u, the du, is 4 dx. Now if I write this integral in terms of u, I can write cosine of u. So that takes care of the cosine of 4x, but you see I still have to account for the dx. So what I'm going to do here is the dx is what I have to account for in the original integrand still, so I'm going to solve for that. So I have 1/4 du. So I'm going to replace this dx with a 1/4 du. And then I bring the 1/4 in front. I just have cosine of u du. We all know how to integrate that. The antiderivative is really simple. It's just sine of u. So the antiderivative of cosine of u is sine of u. I have my plus c on my 1/4 coefficient. And then the last thing that I'll do is replace that u with the original 4x that I use as my substitution. And there's the antiderivative that I want to use there.